All right. Hey everyone. It's been a while. How are midterms coming along? Kinda, kind of okay. Yeah, nice. Or are there particular things you're excited about or enjoying midterms wise? How are you liking working in groups? Is that nice, or is it frustrating? You can like open up right now. Just be like, I hate my group, especially if they're not here right now. um, Yeah, no, I am interested though, because it's like, I'm assuming it's probably your first time working on a software project with a group of people. Are there particular things that are different than like other group projects you've maybe done in your life before? It's all new. I mean, it's all the same. Like nothing new. Hmm. Okay. Yeah, so there isn't like one person. Mm-hmm. Mm-hmm. How are you feeling about like if you run into merge conflicts yet? Yeah. What's that journey like? I see your head nodding. So it wasn't fun. Yeah, yeah. Did you find any like tactics or strategies that made it easier to deal with something like that? Absolutely none. No. Okay. What's that? um. So most of y'all are using Sublime at this point, I think. Is anybody using VS Code? Hey, VS Code. Woo. If you didn't put up your hand, get with the game, man. No, like VS Code is great. Part of why I like VS Code is because of this little thing right here. Anybody using this? No? Check it out. There we go. Look at that. It shows you diffs between like the last time you committed and what your current state of the thing is, right? This is interesting because before you commit, so these are my changes. It's like as if I ran git status, right? Before I commit, I can see what changes I have and verify that okay, I wrote this 10 hours ago. This is an uncommitted change. Am I really happy with this, right? And I really want to stress that like as you work forward, maybe for the rest of the midterms and also when you get to the final projects and something you'll probably find useful in the assignments as well, is that when you commit, there's not just so much that like, oh, okay, I'm proud of myself, time to commit, yay, or like, oh, I don't want to lose all my work, time to commit. Um, you should also check to see like what exact lines do I add to the project or to the code, right? So I do really recommend either like going git diff, right? You can run git diff in the command line and see what pops up, or just use VS Code because it's got this handy little thing where you click on the fellow over here and it shows you, okay, well, Nima added all these lines and specifically deleted this line right here, right? And verify if you're accidentally committing weird stuff. Part of why I'm showing you this as well is because in the context of a group project, you can install little tools like a tool called GitLens. GitLens, it's like LENS, for VS Code, and it looks a little bit like that. And what it does is once you install it, it gives you the ability to click on any line of code and see who wrote it. And Bhaskar rewrote this 30 days ago, right? You wrote this a few seconds ago, apparently, right? Like, I could see all this stuff. And now, why is this useful? Well, you might be working on a project. Suddenly, one line of code doesn't make any sense. You click on it, and you're like, ah, Brenda wrote this 3 days ago. And you can call up Brenda and be like, Brenda, what is this code? What does this mean? Why did you do this? Right? So it's useful in group situations, as well as I mentioned merge conflicts. Figuring out merge conflicts in like a non-visual kind of interface, I find really tough. When you use something like GitLens, when you run into a merge conflict, it'll pop up right here, a little button that says, do you want to accept their changes coming in? Do you want to reject the changes coming in? And you can just click on it and move on with your life. Right? It makes dealing with merge conflicts, if not a breeze, at least a little bit easier. So I wanted to talk about that real quick. And then we're going to hop into today's lecturino here. So, who knows what today's lecture is supposed to be about? User authentication, yeah. And we're like, okay, have we done user authentication before? Kind of. Do we want to retread all that stuff? Maybe not entirely. Like, I'm not going to go over what cookies are again and how a login flow kind of works, because you've done that. You did that for Tiny App really early on. So instead, what we're going to do is look at a couple different topics: security, encryption, I don't know, the privacy. It's social engineering. We're going to look at did I spell engineering right? I think I did. So we're going to look at a couple different concepts, not necessarily fully related to each other. And like I said, don't worry too much about the content of this lecture after today, or after the lecture. Focus on your midterms. But you might find some things today that you think are interesting, and I invite you to look into them. I'm going to open up my notes here. So from my script, the last time I ran this, number 1 was midterms, and we've already kind of talked about midterms. Number 2 on my script is who am I, but you've already had a lecture with me, so I can't really do that. Number 3 was shout out to James Bridle. So does anybody know who James Bridle is? He's only the coolest musician. No, okay, he's not a musician or anything. He's some dude on the internet. He's a journalist. So you go James Bridle. And he's this dude right here. So James Bridle is like a journalist, writer, kind of artist person. The reason that I shout out James Bridle here is because I think in this discussion about, we're going to talk about like security. I think it's interesting to look at how security affects people not in technology, right? Such as leaks of data, right? Who gets access to private stuff, right? How do we ensure that people don't access our secret things? Anyways, this fellow right here, James Bridle, has a really interesting book called New Dark Age. And I've been shilling this book for everyone. It's really good. It's like really, really good. I have a PDF copy, DRM free if you want one. But we're going to cycle back to this later on in the lecture because I have some things that might be interesting to talk about here. The thing is, like, when we're developing web applications, are storing people's data, right? Nice tasty data, data, right? And we got to be careful about how we store that data because some people should have access to that stuff and other people shouldn't, right? Now, let's quickly kind of retread over how we New Dark Age. Okay, how did we deal with secure stuff earlier? How have we dealt with secure stuff in boot camp so far? Do you know what I mean by this question? Yeah, we got passwords. Cool. And what did we do with the passwords? We hashed them. Cool. What does hash mean? Mm-hmm. Mm-hmm. That can only be unhashed by a specific program. Now, is it just a specific program, or is there a little bit more to it as well? Because to hash, we need a program, and then is that it? So usually there might also be a secret key as well, like some kind of salt, salt or whatever. It would be like a secret key added to it. Cool. So Why don't we want to store just plain text passwords? What is bad about them? Yeah, so plain text, people might be able to access that data. So yeah, sure, people's passwords, but like, how? Mm-hmm. Cool. Anyone at the company, right? The call's coming from inside the house, kind of thing, right? Like anyone at the company can do it. Right. What else? Sneaky, smelly hackers. Yeah, sneaky, smelly hackers might do like data dumps, right? You might somehow hack in, dump the database, right? Let's get a printout. I'm in, right? If it's a bunch of hashed stuff, and I don't have the methods for unencrypting that stuff, that's useless. It's just a bunch of random numbers and letters. You want random numbers and letters? I got one, B7, right? Like that's it. So a data dump without the corresponding stuff to unhash it is worthless. So that's part of why we don't want to store stuff in plain text. Now, what else did we do when we were dealing with secure stuff? So we use passwords. We use passwords specifically to log in. Can somebody take me through the login flow for how that worked in TinyApp? By the time that you were done with TinyApp, how did it work? Mm-hmm. Mm-hmm. Cool. And this part here, can you expand on this one? What does login mean? Mm-hmm. Save a cookie, saying that they were logged in. Right? So we started off by storing like their user ID. Right? What did we move on to doing? What did we store in the cookies? What's that? But after that, because we did user ID, and then TinyApp kind of throws a wrench at you, and everybody goes like, shit, and you have to like do a whole bunch of stuff over again, right? What was that part? Yeah, so we save the encrypted user ID, right? We do like a session cookie. You have like a big old kind of encrypted object, right? The user on the front end can't read, right? The user on the front end, if they go look at it, they just see this. They're like, oh man, I can't read this, right? But the server has a way of unencrypting that, right? So it can store information in there and read information out of it. Why do we want to do that? Why did we want to encrypt a cookie? Mm-hmm. Cool. So it prevent people from guessing cookies and therefore editing them to log in as other people, right? Spoof, pretend I'm somebody else, right? Because we could do that before. If we saw user ID 32, haha, I'm user ID 56 now because that stuff is editable, right? Whereas here, if you try to like edit even one character of this thing, it's no longer valid, right? It's like a broken thing. It won't be able to be unencrypted because it's worthless, right? You have to unencrypt it first, then edit it, and then encrypt it again. Is that me? No, it was somebody else. So I get to be like, hey, you, it was you. No. Yeah, so we'd have to like unencrypt it, then edit it, and then encrypt it again. Otherwise, it's worthless. We've ruined it. We've corrupted it. So this whole situation here, yeah, part of it is to prevent people from guessing cookies. But also, when we transfer data. Like when we transfer cookies through the HTTP protocol, like it's going through a wire, right? It's going through a little cable somewhere, little electrical signals. Now, an HTTP request is going to be like a verb. It's going to be the route it's going to. So like get/dogs, right? Plus, it's going to be a bunch of maybe data that's passed in with cookies are passed there, right? So cookies are just packaged in with every request, right? So the server can take a look and say, okay, like who's making this request, right? What's some stuff I should know about you, right? So if the cookies were not encrypted, right? If we just had like the information coming through as name, Nima, age 1,003, height 6'4", and you know all this stuff, right? Other info. Anybody who has like physical access to the wire, or anybody who's like on the network, anybody who's in between me and the request that I'm making too, right? Can listen to it, right? They could pick it up and read it and go, ooh, okay, and pass it on, right? So I think you're like in a classroom and you want to send a note all the way over there being like, I think Nima's really cute. And you write it on a piece of paper and you pass it off to, I don't know why I came up with that example. you're like, Pat, I wasn't going to be, so you pass it off to somebody, right? And you're like, don't read it. And they're like, yeah, okay, I won't read it. And then they read it and then they move it on, right? Like they read it, they violated your request. But you wouldn't know, and the person at the other end wouldn't know, right? And they've read your secret message. Instead, if you had encrypted that stuff, anybody in the middle, even if they try to read it, they won't know what's going on, right? And they have to just keep passing it on or maybe drop it or whatever. So that's something that we have to worry about, right? Is that like we're passing these messages along, like any network request, right, is just a packet of stuff that's being passed along, and it's really just a long game of telephone, right? And we have to trust that the people in the middle are going to be honest, right? Going to be honest, and they're just going to continue giving info, and that they won't tamper with it in the middle, and that they won't read it, right? Now, can we trust people? Whoops. Can we trust the world? Probably not, right? Has anyone ever seen there's a specific, I base my whole life around memes, and there's trust no one, not even yourself. Like, there you go. This is the way I live my life. Trust no. Yeah. So we can't trust anyone, right? And we have to come up with foolproof ways of making sure that even when you don't trust the people around you, you can still get work done. Because we can't just be paralyzed by fear all the time, right? So here's a problem. It's called the Byzantine. I got this. I'll just go Byzantine problem. It was called the Byzantine problem. All right. So there's a thing called Byzantine fault tolerance, or Byzantine generals problem. Here you go. Hill? Okay. So the Byzantine generals problem. This is kind of like an analogy that's going to help us maybe understand a little bit better, like the issues of trust. Is say all of us, we decide like let's raid a I guess a city, right? The 14 of us that are here, we form a little bit of a crew or whatever. Each one of us has an arm, like a little kind of platoon or whatever, and we surround this big old castle. Right? It's a pretty big castle, so we're like pretty far away from each other. We can't really talk as we would, and we don't have phones because it's like ye olden times, right? We need to coordinate an attack. We need to coordinate an attack that should hopefully lead to victory, or we should all coordinate to leave if things are going poorly. Like, we need to make a decision, either attack or retreat, right? And we need to all agree on that, right? Because if there's some disagreement, or if some people are retreating while other people are attacking, it confuses everyone, and we're like, oh no, then before you know it, we've got mass panic, and our operation was a failure, right? So the thing is here, communication between each of us is going to be difficult because we've got physical separation between us, right? Physical separation. So we're going to be sending messengers, right, back and forth to us. It takes a little while to communicate. The other thing that makes it difficult is we've got some traitors in our midst, right? Some of y'all are rats, right? Some of y'all are moles. And, trust no one, not even yourself or, your friends, apparently, because you're all my friends now. So there might be people, right? There might be some of you where when you receive the message of like, hey, we should attack, or hey, we should retreat, you decide to do the opposite because you're a jerk, right? And it might ruin everything for all of us. So this problem kind of goes to illustrate that, like, if we all wanted to form consensus, right? So I went, hey, okay, I decide that we attack, and I tell you, okay, we attack, and then you're supposed to parrot off to to the next person, we attack, and we attack, and we attack. Somebody in the middle might go, hey, like, we retreat, right? And before you know it, we've run into this problem. So there's a couple different kind of ways to go about not necessarily solving this, but mitigating it, right? Which is like coming up with more than one step of a thing. Like you start off with like a null state. To be honest, I don't fully understand how that works, but another way of doing it is just never making a decision ever, or coming up with a default plan ahead of time, being like, okay, everyone, like, if you don't trust the message coming ahead of you, right, just tell everyone that, like, I don't trust the message that had come ahead of me, and we'll just go with the default earlier plan or whatever, like a fallback. Really, the only thing I'm trying to illustrate here is that making sure that messages are passed appropriately can be tough. Now, we are going to talk about a couple different methods for encrypting messages that get passed back and forth. One of them involves what we call like a private key. Right? Sorry. So there's a method called rote 13, which is a letter substitution cipher. Has anyone seen rote 13 before? Cool. That means I get to teach you something. So if we wanted to talk with each other, but we didn't want people in between us to understand what we were saying, right? We might pick, actually, does anybody have a piece of paper I could borrow? I just don't want to rip something out of my notebook because they matter a lot to me. Here. We're going to do the demo live. All right. Can I have a volunteer? Oh, I should have looked up. Nice. All right. All right. So keep it secret. Yes. I mean, you can read it too. Yeah. So nobody saw that secret shifty exchange of of cash. So I'm going to ask you a series of questions. And first everybody's going to answer except for Dan, and then Dan's going to answer with Dan's reply. So first question, what is 7 plus 3? Cool. Dan, what's 7 plus 3? Oh, snap. What? Oh, man. All right, we got a little bit of secret conversation going on here. What's the day of the month? Yeah, yeah. Sorry, what's the, like, what's the word for that when you want to say like the number, but like in the month, but like, I'm total like ESL, by the way. I'm like Italian, so but that's not really an excuse here. Anyways, the day of, what's this number that I'm pointing to with my mouth? 21. Damn. Oh, what? 23. Oh my God. Okay. Well, what minute is it right now? Okay. Damn, what minute is it? Huh? It should work. Like 36? Let's just say it works. All right. So apparently, I mean, hey, learning, huh? Yeah, 48. See, it does work. Yeah, yeah. It's 48. So does anyone have any idea what's going on with the communication between me and Dan? Yes. Mm-hmm. 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 Exactly, right? Exactly. Some number that like he knows, I know, but the rest of you don't know because of the thing that, like you said, is written on there that says add a certain thing. Now, maybe given enough questions, right? Maybe given enough questions where you know what the initial answer is and the final answer is, you'll be able to figure out how to translate between the two, given enough of those, right? But off of the first few couple, you have no idea. Like, does anybody here have any idea what the clues on the piece of paper might be? Probably not, right? What are the things on the piece of paper there? Huh? Yeah, well, like, what are the keys there that I gave you? Yeah, right? So we made it a little tricky there for you. But hey, I mean, I think you're clever enough. After like 100 or 1,000 of those, like you might have figured it out. You start bringing statistics into this and see like what are the trends here or whatever. But it's an algorithm, right? Which isn't necessarily safe because the more it gets used, right, the more clear it is about what's going on, the more transparent it is about what's happening there. Right? So this is an example of something that one might call a cipher. So I mentioned rote 13 earlier. With rote 13, we have all our letters. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and these ones as well. No. Yeah, he comes. Oh, no. So has anybody ever seen, like, Zalgo before? No? I'm not going to bring more memes into this. Anyways, if I was to split this, like, right in the middle, right? If I was to split this right in the middle and say, hey, anytime an A goes in, right, give me an N. And anytime a B comes in, give me an O. Right, whoops, O. Right, we're seeing, like, the pattern, I hope, right? Any one of these will map to the corresponding one here, and any one of these will correspond to the one over here, right? So a message that might be like "so dude," right, will translate out to F, H, U, and then a space, and then Q, and then H, and then Q, and then R. And you look at Fahu Kakur, you don't really know what's going on, right? But with enough of these messages, right, enough of this stuff going on, you can start going, hey, you know what? I feel like we can start trying out some stuff here. What's the most common letter in the, the most commonly used letter in the English alphabet? Does anyone know? E, right? And I can say, hey, you know what? We can start looking for some E's here. Now, in this case here, there's 2 U's and only 1 E, but with enough writing, right, I might start seeing that some particular letters are used more than others. And I could say, hey, you know what? How about we just act as if that's an E? Right? And then I work my way down. I'm like, okay, well, what's the second most used one, right? Maybe it's A, I think, or whatever, right? And we start replacing things that way. And it's essentially just like the Price is Right. Not the Price is Right, the Wheel of Fortune. It's essentially Wheel of Fortune. You're just figuring out like what could it possibly be statistically. So not very safe, but it's good enough for like a one-time kind of communication, right? If you don't have anything, like any buildup of data, right? Or if I just need to do like one quick message, it's fine, right? It's fine. Now, so rot 13 kind of means rotate by 13 every time, right? Just rotate forward 13 steps. To bring it back to the example that we just did right now, right? We were moving numbers back and forth, right? But just imagine that each number was associated with a particular letter, right? And now all of a sudden I can actually communicate. It would just be like one letter at a time, right? Computers move a lot faster than people do, though. Computers ask questions a lot faster, so it's more efficient. Now, there was one thing, though, that Dan and I had to do in order to have that secret conversation, right? What did we have to do? Yeah, I had to physically somehow make sure that Dan had the algorithm and the rest of you did not, right? Because that would have defeated the purpose if I was like, hey, can you actually pass it over there, right? Like, no, trust nobody, not even, the person next to you, right? Trust no one. So I had to figure out some way of exchanging that key, right, over to the other side. I did it by physically walking over. Can't always do that all the time. Can't always, like say you wanted to use Facebook, right? Like you go here, you're like, oh, time to register for Facebook.com. Why, yes, I would like to sign up. Mark Zuckerberg, here's my blood type, oh, negative, and whatever. It's my parents' address and all that. And then you click sign up. And the thing, instead of signing you in, it's just like, all right, can you give us your address? And you're like, oh yeah, here's my address. And they're like, okay, it'll be 6 to 15 business days. And 6 to 15 business days later, you're at home and the doorbell rings and you're like, oh, I just got my Facebook login info. Oh, I'm so excited. And you go open up the door and it's Mark. He personally delivers every one of these, right? He's like, trust nobody, right? Like, and he gives you like a little manila envelope and you open it up and it's in like gold foil, right? I'm like, wow, this is my password, thank you. I'm glad we did the secret key exchange, right? Obviously that's not doable, right? It's stupid, it can't work. We need to figure out like a smarter kind of electronic way of transferring that stuff. And we will. It's going to be called the Diffie-Hellman key exchange. All right. And I'm going to put a note here, Nima's soapbox for a minute, James bridle, and then also Amazon snowmobile. Has anybody heard of Amazon snowmobile before? Okay, this stuff is bananas. So we're taking like a quick tangent, very quick, hopefully. So when you got like stuff you want to put up in the cloud, like I took a couple cute pictures of my dog. Time to put them up on the cloud so they're like stored there, nice and safe. Right? You go to whatever and you upload and it's good. It takes maybe 10 seconds, maybe less. That works out fine. Maybe you've got a hard drive with like your backup of everything you've done this year. Maybe you edited a lot of videos and stuff, so it's like pretty big. You got like a terabyte hard drive. Like, all right, I'm gonna upload this to the cloud. It takes a while, right? You plug it into like Google Drive or whatever and just pay a little bit, upload all that stuff. Might take an hour, 2 hours, really quite a bit of time. Still within like reasonable kind of limits. Now, say you're a company with like petabytes or exabytes of data, right? Like just insane amounts of data. And you've been storing this stuff on like your in-house machines, right, and your own in-house like storage. And like, I want to transfer this stuff to the cloud. Our business is going to the cloud. Now, you can't drag and drop a like 1 exabyte file into, you know, and just be like, all right, like time to, yeah, that stuff genuinely takes years to transfer on like a fast connection. It takes like years to transfer on through the internet. So Amazon came up with this thing called snow machines. Okay, so they started off with a thing called Snowball, where they would send you like a big kind of drive, right, in a box, and you can hook it up to your machines, and it's fast to transfer stuff on like local, right? You can do it as fast as you want, like super fast. You fill up this machine, it may take you a day or whatever, right? And then you ship it to Amazon, they connect it to their servers, right? And they can upload your stuff from there, right? So it still involves like a physical kind of transfer, and all that stuff is encrypted. So if, say there's like the person walking with the hard drive that's all encrypted and they get mugged or whatever, like you don't lose your data, like, or like a raid, like a bandit raid on, like you don't lose your dog pictures. It's fine because they're encrypted. You can just do them again. Now snow machines. No, snow machine, snowmobile. Snowmobile. Stuff is madness. They drive a truck to your business and they hook it up. They hook up a truck to your machines. This this whole thing is a hard drive. And they download your stuff and then they drive across the country to the to the like AWS stores. This was them like revealing it to like at a conference. Honestly, like it's just straight up bananas the way that like.
A number of our customers said, "Well, this is great if I have."
Just got to go forward to where he reveals the truck, because he makes a big deal about like we've come up with a new technologically advanced way to transfer data at high speeds. Instead of taking 26 years to transfer like however many exabytes of data, it will only take you 6 months. And he's like, we're gonna need a bigger box.
Allow us to move exabytes of data so we can leverage the cloud as well. So we thought about that. That was a tricky one. And the first thing that came to mind was we're gonna need a bigger box.
Just drive out a truck. Yeah. It's like so cheesy, right? Yeah, and it just keeps going. Like it's just constant. Yeah. And the dude walks out and he's like, "We got a truck." What I love about it is it's not like branded or anything. Like you don't even know if there's anything in there. They're like, "Yo, could we just rent a semi for this conference?" Like we haven't actually built this product. Like we just rented a U-Haul. Like, no, I don't know. That's tech for you, eh? Like, cause I've never heard of that happening. Yeah, I mean that would make sense. Yeah, it wouldn't be like, hey, we have data here, like, but this is the kind of stuff like, I'm just imagining like a Borderlands style world, where there's just caravans of people, or think like Mad Max, like Fury Road, except instead of transferring like the women to the promised place or whatever, the green place, it's like data. Like we gotta get the memes there, like you know. So I don't know. This is the kind of stuff. Yeah. All the knowledge, yeah. No, we should write a script. But I mean, this is kind of related to what we like to the lecture, right? Secure data transfer, it has to be fast and whatever. Will you, in the next couple months have to deal with Amazon Snowmobile? Probably not. But maybe one day it's feasible, right? Like, there is like an API to schedule a little truck to show up. Anyways, so that was Snowmobile. Check. What time is it? 9:51. Okay, we're gonna take a break. We're gonna take a quick break, and then when we come back, we're gonna talk about the Diffie-Hellman key exchange. Although, are there any questions before I let you go? No? Coolio. All right. All right. So I'm gonna pick up again. Um, yes. So we'll get back into again. We'll start off with the video, and then I've got a little bit of stuff to talk about. And then I mean we're not gonna go the full 2 hours. Usually when I lecture, I go like 2 hours. It actually took me months. I think I worked here 6 months before I found out that other lecturers don't do 2 hours. They do like an hour and a half. Um, so I'm like, hey, you know what? It's my time. I'll tell my jokes. I'll show my memes. You know, like I fight me. Like it's so. So what we're gonna do is we're gonna watch this video about social engineering. Great. Does anyone know what social engineering is? What's social engineering? Yeah. Yeah, exactly. Like using like real life, like out of computer ways to do that stuff, right? So seeing somebody's password like written on a sticky note, or um, yeah, um, through human error. Sure. Like, can you expand on that a little bit? Yeah, by being like really charming. Like, huh? Con them. Yeah. Like, hey, what's your favorite like credit card number? Right. um, that's like good first date talk. Like, oh yeah, what was your first credit card that, what's that? What's your first pet's name? Yeah. What's your mother? Yeah, tell me about her maiden name. Yeah. Um, so, so here's the video.
So I invited a few of the world's best hackers to try to hack me and show me where my vulnerabilities are. And now I'm going to meet them in Las Vegas for DEF CON, the biggest hacker convention of the year. They're going to have me using social engineering, which is essentially hacking without any code, just using a phone and an
Volume's like really
application.
low.
You want to do a sample phishing call?
What's phishing?
Phishing is voice over switching. And basically, what you do is you use the phone to extract information or data points that can be used in a later attack.
Let's do it. Okay. Who are you going to call?
Maybe I'll call your cell phone provider, see if I can get them to give me your email address.
I bet they're good. I bet they have my back. But yeah, go for it.
I'm going to spook from your number, so it's going to look like it's called phishing.
Okay.
Hi, I'm so sorry. Can you hear me okay? My baby, I'm sorry. My husband's like, we're about to apply for a loan and we just had a baby and he's like, get this done by today, so I'm so sorry. I can't call you back. Log into our account for information and I can't remember what email address we use to log into the account. Are you fine? Um, awesome.
In just 30 seconds.
Email.com?
Just it's access to my personal set up her own personal access to my account.
Yeah, sorry. So there's no password on my account right now. Can I set that up?
She even gets the support where she would change my password.
Thank you so much for your help today.
She just basically wants me. I was like,
I'll get her set up. All right. Thank you.
holy shit. They just gave you access to my entire cell phone.
You're gonna have to go over and change your password. Yes. My name.
And all it took was a crying baby.
That stuff is bananas. It's crazy. Trust nobody. um, mhm. Mhm. Wow. And how did the training go?
It was basically, unless this person is the person, the account holder, or noted in the notes on the account as contact, don't tell them anything. The only thing they can do is use something.
Mm.
They can give you their credit card number
And that's just one place.
Yeah, that was of all places.
Impart, man. For,
for their master session.
okay, man.
Every other call center I've ever called being like, oh, what's your thing? Blah, 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 blah. Okay. My friend recently told him for his wellness account, I don't sound like Eric Olson.
Man, that stuff it's scary. That's the world, right? Like so much runs on this stuff, and it's so loose. Yeah. So yeah, the other day the advanced lecture was on ethics, and like ethics of technology. So I'll do that for your cohort as well off in January. We'll get together and we'll talk about ethics. And one way in which technology and ethics intersect is here, like through securing data, like making sure that like people don't get access to the things that they shouldn't get access, right? How much effort do we need to put in training people or in like designing systems and stuff? So that's something that like you can talk about when we get to the ethics lecture. So surprise, off in January. So you got some time to like brainstorm. Try it, and then I wanted to say, oh, I got this. Two-factor authentication. Okay, so there's not going to be any actual coding in today's lecture. We're going to look at some examples of code, and I'm going to talk about a couple more things. So first, I'd made it to the Diffie-Hellman key exchange. So earlier, when Dan and I had a secret conversation, I had to walk over and give him my piece of paper with the key on it. But there's a method called the Diffie-Hellman key exchange for transferring secret keys. And I'm going to Google Diffie-Hellman key exchange. Now look at this, handy dandy colorful diagrams. This is going to be, oh, I want this one with SpongeBob actually. Actually, this is not a very good diagram, but like, I don't want you to have to think about the math. Like, you're gonna look at this other one with paint instead. This one's a very good diagram. There you go. Okay, so wow, not good. Okay, all right, we'll zoom in on this. All right, I know the text is really small, so I'll read out what it says. Let's imagine that there is a person named Alice and a person named Bob, right? Usually when you look up like cryptography stuff or security stuff, there's always in the examples Alice, Bob, and Sneaky Eve. Very sneaky Eve. So right now we have Alice and we have Bob. Alice and Bob can agree in public on a common like paint color, right? Here is yellow. Awesome. So Alice and Bob out in public, they declare yellow, right? And it doesn't matter if other people hear it. It'll just be like yellow. Okay, cool. Then in secret, Alice comes up with their own color, and Bob comes up with their own color, right? But these are secret colors. Now, both Alice and Bob mix the colors together, right? Mix the common color with the secret color that they came up with together, and they end up with something else, right? And now these things can be transported in public. I could be like, oh, can you pass this down there? I don't mind, right? Because the thing is, like, anybody in the middle is actually unable to figure out what the secret colors are, even if they know what the common colors are, right? Have you ever tried unstirring paint before? Yeah, it's not easy, right? Now here we're just going to assume, like, these are going to be mathematical operations where we'll say that addition is really easy, right? Addition's going to be really quick. And subtraction's going to take like 1,000 years. Right? Subtraction is possible, but it just takes forever. So it's intractable. Like it's unfeasible as a thing. So we can transfer these things that have been added together safely in public. We've transferred them. And now I have the mixture that like somebody else has made, and somebody else has the mixture that I made. And when we get that, we can add our own, again, our own secrets that we had in the beginning to them, right? And we end up with a common plus the other person's secret and our secret. Both of us end up with that, right? both of us end up with a common and one of each secret. So we end up with the same thing on both sides, but nobody in the middle would have been able to intercept it, right? Because they wouldn't have been able to separate things, right? Because at any point, I'm only in possession of my own secret as a raw thing, right? I never actually even know what the other person's secret is, but when I then add my secret to their combined common and secret, we end up with a common secret between the two of us, right? I know looking like at this the first time can be a little jarring, right? But the goal of this is that we end up, like two people who've never physically been in the same place, right? Who never physically met up, end up with a common thing that is secret between the two of them, right? But not knowable to the rest of the world, right? And now all of a sudden we've ended up with that, with something that we can use for encrypting our messages the way we did earlier, right? I did not have to like walk over there and do it, or Mark Zuckerberg doesn't have to like come to your house and be like, ding dong, yeah, I got like 1,000 more to do with these today. Like, come on, hurry up. Like, give you like the gold foil password. So this is the Diffie-Hellman key exchange, and it's obviously not done with paint. It's done with math, but the high-level kind of concept works like this, and it's the basis of like public key like cryptography, making something public, right, so that other people know what the key is, right, and also having a secret somewhere. So I do recommend reading into the Diffie-Hellman key exchange. It's interesting. Something neat about it is that this thing had been invented by, there you go. So this thing was published by Whitfield Diffie and Martin Hellman in 1976, but later on in 1997 it was revealed that the British Signal Intelligence Agency had achieved it in 1969, so like well before 1976. Right? This method of encryption had been like of key exchanges had been discovered or developed way earlier. And it was just kept secret from the rest of the world, right? And this is something that is also worth thinking about in the realm of ethics, right? Like, is it right to come up with technology that can be immensely helpful, but keep it a secret from people, right? Because the Diffie-Hellman key exchange, again, it forms the basis of secure, like, information transfer on the internet. Like, makes the internet possible, right? In the sense of like, we can online banking, all that stuff, right? You know, arguably held back like 7 years because they wanted to keep this thing a secret. Right? So that's something to think about as well. Anyways, this is the Diffie-Hellman key exchange. Now, there's this is for that, like, so I used the word public key earlier. I shouldn't have used that. It's a common secret, but it lets us have private keys between us. There is a thing called public key cryptography, though. As I said, Bob, Alice, and Eve show up all the time. So here's Bob and Alice. Now, there's no whiteboard over here. There is a whiteboard over there. You help me wheel it over? Thanks. Is this anybody's midterm project?
Yeah, that's mine. It's okay.
I'll erase part of it. Okay. Yeah. Look how bad this. No, it looks really nice. Yeah. Just gonna move this back a little bit so I'm not like standing in your face and screaming at you. Cool. Oh, my favorite eraser. Oh, I feel so bad. Took pictures of it? Okay. Okay, I did it. So, we have our usual suspects. Alice, Bob, and Eve. Alice, Bob, and Eve. And we've got, so Alice right here. We've got Bob right here. and they want to have like a nice conversation, right? Sup, Bob? Oh, not much. Alice, how you doing? Right? Like secret stuff that nobody should be listening in on, except sneaky Eve. Always here. Little Eve wants to spy on what Alice and Bob are talking about. So if Alice and Bob use unencrypted speak, sending messages back and forth, right, via cable or whatever, right? Eve can snip, a little snip snap of the cable right here, right? Eve can listen, just read all the little messages and then forward them, right? Bob never knows. As far as Bob's aware, that message was from Alice because Eve might not have tampered with it. Or Eve could be extra sneaky and tamper with the messages, right? Alice could be like, Bob, you're the love of my life. And then Eve like sneaks in, grabs the messages and turns it into like, Bob, I hope you die tonight. I hate you, right? And then like puts it back in and sends it off. And now as far as Bob's aware, Alice hates Bob, right? Oh, sneaky tampering of messages. So what we would like to do is, first of all, we talked about private key stuff, right? So if Alice encrypts the message with a private key that both of them know, whether through the Diffie-Hellman key exchange or maybe they met up or whatever, Alice can send a message that's encrypted, and if Eve tries to get it, first of all, Eve can't even read it, right? And if Eve does try to edit it, right, then what Bob gets on the other side is going to be a mess. It's just going to be a jumble of words and letters. So Bob will know somebody tampered with this, right? Does that make sense from what we did earlier? Cool. So instead, with the public key, like public key cryptography kind of method, what we'll do is both Bob and Alice, and even Eve, if you even want, can have public keys, right? Keys that they publish online, and they say, "Oh, what's up? This is my key," right? So you'll see sometimes on people's, like if you go to like journalists or like dev websites, here's a dude named Drew DeVault. Drew DeVault on their website has PGP public key block that Drew has put on their website, right? And anybody can see it. What's the use of this? We'll see in a sec. So people will publish their public keys, and the public keys are going to be generated using like a program or something, right? So public key, this Eve might have a public as well, and so does Bob maybe. They'll use a public. And the way that we're going to use this information is Alice, Bob, and Eve don't just have public keys. They also have their own private keys that nobody knows, right? So Alice has also a private, right? Bob might also have a private maybe or whatever, right? They all have their own private. So the public is published, private is kept secret. Anytime Alice wants to send a message out, right, Alice is going to use the private key and the public key together, right, to create unencrypted message, right? Create an encrypted message, the public, the private key, and there's a whole algorithm, right? And a message comes out, encrypted message. I'll say that the message is X, so E of X, right? Encrypted message. If Bob wants to read this message here, right? Oh no, snap, I lost myself. Right. Okay, so this isn't going to fix exactly the same problems I was talking about before. We'll see how it's still useful, though. If Bob wants to read the message, Bob can use the public key and the algorithm, which everybody knows, to open it up. So can Eve. So can Eve. But Bob is assured that like the message could only have been written by Alice, right? So Eve can open it up, but Eve can't close it up again. Can't close it up again because Eve does not have the private key. So if Eve opens up a message and tampers it, Eve is not able to close it and send it off, right? So the tampering can't happen anymore. Eve can still read it. It just can't tamper it. Bob is aware that Alice sent it. If Bob wants to send a message to Alice, right? If Bob wants to send a message to Alice and doesn't want Eve to read it, and it doesn't want anybody else to read it, Bob can use Alice's public key, right, to encrypt it. Bob can use Alice's public key to encrypt it. Even if Eve snags it, Eve cannot open it up. Eve cannot open it up, so Alice is able to get messages securely from Bob. So if Bob had a public key, Alice had a public key, right, and they all have private keys as well, like they can communicate back and forth without anybody tampering in the middle, right? But the funny part about it is that there's public stuff that everybody has access to, right? Do you see what I mean from earlier on about how like you don't have to worry about this as part of the curriculum right now? I'm just showing you cool things. So in case your eyes are like glazing over right now, like don't worry, it's totally fine. Is it making a little bit of sense? Yes. So Eve could have a private key. Anybody is free to generate their own public and private keys. Here, I'll do one right now. So there's a program called SSH Keygen that you have on your machine already. And if you were to hop into your terminal, and have I shown you all my fish before? Probably multiple times, right? So if I was to hop into the terminal and go SSH keygen, it goes, oh, generating public-private, RSA key pair. Where do I want to save it? Test is what I've named my file or whatever. And then you can give it a secret key, key to even encrypt the secret key. There's no need, just empty. And now, just by running SSH keygen, it's given me, if I was to go into here, a test and a test.pub. Right? And if I was to go, like, this is my public, yeah, and this is my private key here. Right? But there's a whole number of methods in which you could generate pairs of public and private keys. Like the public key and the private key are intertwined, right? They are related to each other. But this stuff is built on math that's like incredibly hard to decode. In the sense that there are mathematical operations which are easier to do than to undo, if that makes sense, right? Yeah. So does that kind of answer that as well? Right? Anybody is free to generate their own. If you go to like a couple people's different websites and stuff, they'll have like Drew Default's blog, they'll have a key over here, and you can go check it out, right? So if I wanted to send a message to Drew, I could encrypt a message using Drew's public key, and only Drew would be able to read it, right? And if Drew wanted to send me a message, right, or rather, if Drew wanted to post a blog post, and I wanted to verify that Drew was the one who wrote it, right, I can check to see whether it was encrypted with Drew's public key, right? So these keys serve two purposes. One is for like secure transfer of information, and the other one is for verifying that that person made that thing. So a lot of the time, just a sec, a lot of the time if you go check out like open source software, like let's check out the download Linux here. I shouldn't have done that. A little download button. If I go to download some open source software, a lot of the time what they'll give you is, yeah, I mean, I guess maybe not here, but a lot of the time when you go download some open source software, it'll come with a key that you can check, right? It'll either be called a checksum, right? Or they'll have like private keys or whatever. Cool. You want to say something? Actually, you can do it even without your own private key. So the math behind it is pretty funky, but what it ends up looking like is, interestingly, if we thought of the encryption as E, as like a function, so here is a message, and I encrypt it with E of x, right? And E is going to involve, let's say that this is going from Drew to me. So Drew has a message, encrypts it. I can unencrypt it with the public key. Okay, so I can take the public key and unencrypt the message. And it's interesting because the unencryption algorithm is actually the same as the encryption algorithm. So you just run the encryption algorithm again on the encrypted message, and it'll unencrypt it. So this part here I do using Drew's public key. So Drew uses private, I use public to unlock. If I wanted to send from me to Drew, what I can do, like with Drew's private and public, what I do is I take Drew's public key, right, public key, and then Drew uses the private key to unencrypt. So X, using the private key again. My arrows are horrible, but I hope you can see kind of the flow. At any time, like, Drew uses the private key on this side to encrypt. I use the public key on this side to encrypt. Right? Drew uses the public, the private key to unencrypt. I use the public key to unencrypt over here. I got that right, yeah. Okay.
Essentially, anyone just unencrypted with the public.
Exactly, right? So for this direction, right, from Drew outwards, the keys are used to verify that the message came from Drew. Not for secret messages, but just to verify that the message came from Drew. For this direction, this is for secret messaging to Drew, right? So it doesn't serve like both purposes in both directions. It's one purpose in one direction, one purpose in the other direction. If I wanted to receive secret messages from Drew, Drew would have to use my public key, right? So the use here is like, say I'm reading an article and I want to make sure that this article was actually written by the New York Times, right? Like verify that this is from them, right? They would encrypt their thing with their private key, and anybody can unencrypt it with their public key, right? To verify that yes, it did come from the New York Times. Or let's talk about like banking, right? You want to say yes, this page was served to me from TD Bank, right? It was sent, like this page was given to me by the TD Bank server, right? And it's been encrypted with the TD Bank thing saying that it came from us. So I like, when you go on some websites, like linux.org, if I click on here, say the connection is secure, there's a two-way thing here. Like I can communicate with the website securely, right? So they've set up a private key thing for the two of us to communicate. There's also just the fact that like I can verify that it's like a certificate. I can verify that this website is who they say they are, right? That's important as well. So not just secure, like secret transfer, but also are they who they say they are? To really kind of point out the distinction between these two things, you can have a secret conversation with somebody who's lying about who they are. Right? You can have a secret conversation with somebody who's lying about who they are, who they say they are. You can also have a not secret conversation with somebody who you are sure is who they say they are. Those are two different things, right? So we want to make sure that both of those things are covered, and the public key protocol like lets us do that. Right? Now, do you have to worry about this as a developer? Like, no, you don't have to worry about this at all, right? You will, like, be using most likely stuff that does this for you, right? But you won't have to implement this stuff on your own. You'll use other systems. Now, it's 10:34. There are two things that I want to talk about fairly quickly. None of them is two-factor authentication. Has anybody heard of two-factor authentication before? Okay, what are the two factors? What's that? Mm-hmm. Cool, so one-time password. Right, so that could be it. We have two factors, one being one password that's like constant, just forever, like we set it, and the other one is just something else. In this case here, maybe the company or the service that we're trying to access also sends us a one-time password. And we have to explore this because, like, how does this one-time password work? How do we get it? Does it get mailed to us? It gets texted to us. What's the value of that? Like, I didn't phrase that properly, but like, why is it important that, I don't know why I'm looking here because the screen's over here. Why is it important that, like, the password gets texted to us? Mm-hmm. Yeah. Perfect, exactly, right? So it accounts for two things. One is something that we know, right? Our password, we know our password, hopefully. And the other one is something that we have, right? Our phone is something that, like, maybe somebody who's hacking into our account or trying to get into our account does not physically have our phone. And our phone is a thing that's registered to receive that one-time password, right? So here to check to see whether somebody is authentic, right? Like, are they who they say they are? We check to see whether their password is correct. Do they know a thing that they should know, and do they have something that they should have, right? You're gonna have three-factor authentication, which is, are they, or let's see. So we go something you know, something you have, and something you are, right? That could be like a third factor. So we could have a password, a phone that a message gets sent to, and also biometric information, right? Like a fingerprint, right? Or blood, or or hair, or whatever, right? Like some other kind of factor. Or I was briefly talking to the dude who has a startup. He's a sketchy guy. I don't like him at all. But like, I really didn't like him. You meet sketchy people. Have y'all met sketchy people before? Probably, yeah. No, so he just kept like buying chicken wings for me. Like, yeah, he was interested in like hiring me for this thing. And they did like web security, and I'm like, I have no experience in web security. And he's like, oh, it's fine, right? Like, it's okay. You know JavaScript? I'm like, I guess so. And he's like, oh, it's gonna be great. And here's my partner, and partner shows up. We were like at a bar. He starts making like pro-Trump jokes and stuff. And I'm like, oh man, like I'm Persian, dude. Like the travel ban like just got put on. Like, I'm like, my grandparents can't visit my cousins. Like it's not fun. And he's like, no, it's hilarious, man. I'm like, I don't know. I don't want to work here anymore. And they kept buying chicken wings, and they kept buying beers. And I'm like, dude, like I drove here, like I have to drive home. They're like, oh, like you're not being fun. Like keep buying. You're like, well, we're buying. Like keep drinking. And then they kept like hitting on the servers, which when you're like at what is essentially a job interview, but like eating chicken wings and drinking beer, and like in between these two people you don't like, and then you're like, hey, welcome to our sleazy kind of interaction. But I did not agree to this at all. Anyway, that aside, this dude has this startup, and they did. I'm not gonna say his name, but like, they did a. Yeah, if you get an offer from a cybersecurity place, just come ask me first if it's the dude, and I'll tell you. Anyways, they did cybersecurity stuff, and among the stuff was they wanted to implement a system where, like, for extreme security, it's not just a password, it's not something you know, it's not just something you are, like, it's all that stuff. Plus, the system would, like, have to notify, like, a person who knows you, like your mother, right? And it would put like a video chat, right? And the other person would have to be like, yes, this is David, or like, yes, this is Luann. Just imagine every time you had to like sign into Facebook, puts it into like a video call with your mom. Like, yes, I just wanted to see some memes. I guess I'm sorry. But no, they were doing it for like high level bank stuff or whatever. But the multi-factor authentication is something to think about. You might be in a place where you have to implement something like this, right? Like not just password authentication, but also using a system to like connect with a phone or send out a text message, right? That kind of stuff. Look into Google Authenticator. So reason I bring this up is because you can also talk about something that's loosely related, single sign-on. Has anybody heard of single sign-on before? No, but you've all done it. You ever signed into something using Facebook or using GitHub? There you go, right? Like signing into a service by using another service's authentication flow, or authentication flow. So is sign on with Facebook, GitHub, Twitter, Google, all that stuff. What are the benefits to doing something like this? Do you know? It is really quick, eh? Yeah. Quick. Easy peasy. Yeah. What else? Yeah. Do you want to expand on like what does that mean? Mm-hmm. Yeah. Right. All these companies, as you said, have already dealt with these problems, right? So we can offload that work to them, right? Do we have to then store passwords? No. Somebody else stores the passwords. Right? I just don't have to worry. I just sign in with Facebook. Facebook will tell me if you're signed in or not. That's okay. Right? That way, if somebody tries to hack, it's not on me. It's on Facebook. Right? Are there negatives to this? Mm-hmm. Not want to give them, right? So when you sign in with Facebook or when you sign in with Google, you get a little like a teeny little notification, light gray italic text. It's like, oh, by the way, they now know all about whatever. Or you're like signing into a system with Facebook and it says, oh, this gives the app the ability to post to your timeline, right? Like message people. I'm like, what? No, like I don't want that at all. Hey, I'm just trying to sign into a service. I don't want to post about this on my Facebook statuses. Like I haven't written a Facebook status in like 4 years. I'm not doing this now, Farmville or whatever, right? Like so exactly, right? We don't want to give them access to our data and also control of our accounts maybe sometimes. Yeah, exactly, right? Oh, a little person. All right. You ever see the little smiley face down here? You have a little smiley face at the bottom of VS Code. You can click on it to give feedback, to like tweet feedback at them. But I like when I'm coding and I'm having a hard time, I just look down here and I'm like, it's all good. There's a nice little friendly face. Sad face, no, happy face. Wow, sad face takes up less characters than a happy face. It, it takes more energy to be happy than sad, apparently. I'm forever sad. So yeah, sharing all our data. There's also just the fact of like who's responsible in case of a breach, right? Who's responsible? I'm not the one holding the data, and Facebook is, or Twitter is, or GitHub is, right? I'm not relying on them, right? And that takes a little bit of control away from me as a developer. Just stuff to think about. Still, though, super convenient. Might as well use it. And the way in which we'll use it is using code that Nima didn't write over here. Nope. Oh, I got this. I'm going to find this. Here you go, one. Back. Oh. Nope. Almost. There we go. Okay, yes. No. Damn it. There we go. Okay. So there's a thing called passport, right? There's this thing called passport.js. It does simple, unobtrusive authentication for Node.js. Have we used Node before? Yeah. How useful is that? Cool. Passport authenticate. GitHub. Twitter. Easy. Apparently this is all you have to do. Okay, this is a little bit more. But what Passport is going to be is it's middleware. And we've used middleware before, right? Where did we use middleware? Express, right? The Express middleware, right? We used like cookie session middleware and body parser middleware, right? So here's the Passport middleware, right? Just drop it into any Express-based application. 500 plus strategies now. Let's check out the documentation. Okay. So you'll be able to npm install Passport locally in your system, right? And then any route that you want to hide behind like authentication. This one in particular, like this /login, this is the callback that's being passed to /login, is it'll go through authenticate, right? And if authentication works, it'll redirect you to /. And if authentication doesn't work, it'll redirect you to /login to try and log in again. We can go down a little bit to see where the, I mean, I have an actual example of code over here, which we'll take a look at. Oh no, I dragged it over. There we go. Cool. So, oh no, we lose all of the syntax highlighting. Oh no, I have an idea. Copy this. Go over here. Make a new file. Passport.js. Easy. Syntax highlighting. Okay. So this is a Express app like you're used to seeing. var express equals require express. And then here's Passport, which we required in. We also require in another thing, passport-facebook.strategy. Okay? So with Passport is a system that lets us take many different sign-on strategies, right? Whether it's Facebook or GitHub or Twitter or LinkedIn. We can take all those, right? Pack them in maybe together or decide to use only one of them. So here I'm requiring in the strategy for Facebook. And I say that Passport should use that particular strategy. Right? So here we'll make a new strategy being like set up with maybe all this stuff that I'm doing myself, like maybe pointing to the like my Facebook ID and secret that I have to get from configuring online. And then I can make a bunch of little methods for what happens when trying to like serialize and deserialize users in and out of the session, or like encrypted cookie session that you were doing before. But you skip past a couple of things. The idea here is we have that app, right? Like we've done in Express so far, and we pass in Passport as middleware into the app, right? App use Passport initialize. And then anytime that we want to pass through the authentication, right, we can pass that in as a callback. Right? App-get login Facebook gives us this, right? Or profile is protected. So we'll say that before you run this callback, right, which renders the profile, we have to require the fact that let's make sure that the user is currently logged in. Now, I don't want to dive too much into exactly how this works because there's many other tools that you can use to set up authentication, and I don't want you to feel like you have to be married to Passport. Like you don't need Passport right now or really any time in the boot camp, right? But when you go work somewhere, you're going to have protected routes, right? You're going to have protected routes, and if you're working in Node, the way that you make sure certain routes are protected is you'll put in middleware, right? The middleware is going to live between the request and the response, and it'll check to see if that person is authenticated or if they need to go be authenticated, right in the middle there. I think you did something similar with TinyApp, right? You have to check to see if the cookie exists, right? That's technically like checking to see whether somebody's authenticated or logged in. The thing about that is that you were probably writing that directly in the routes. You probably had inside of this thing, if cookie.user or whatever, right, then redirect, otherwise whatever, right? You had it written for the particular routes that you needed in here, in here, right? If you have a million routes, right, a million pathways, then you're going to have to rewrite this thing over and over and over again, right? You might as well take this and put it in middleware, right? So it always gets run, or it gets run on most routes, right? That's one thing. And you might also just not want to write that code yourself, so you bring in a library like Passport, right? Again, I know I shied away from really explaining how Passport works. I did that on purpose. If you're interested in it, the documentation is really good, right? And I'm also going to send you links to one of the other lecturers' notes where they actually dive through how to use Passport. Right? Not next week, but when you come back in the new year, you're going to be starting off with Rails eventually, right? The way authentication works in Rails is going to be pretty similar, right, as Flow, but you'll just find that stuff lives somewhere else in the program. I mean, really, that's about it as far as what I have for today. 10:52, so I guess I did use quite a bit of time. Do we feel good about this? Do you feel like you've learned something? Right? I thought you shook your head. Like it was like a vigorous like head shaking, but you were just looking at the screen. So for a second, I'm like, wow, that's really open. Wow, okay, that's immediate feedback. Just no. So again, don't worry about taking this stuff and integrating any of it or any of this knowledge into the rest of boot camp. Just stuff that you might want to like read up on later on. I'm gonna be here for the rest of the day if you need help with midterms. Yeah, have a great rest of the day. And actually, have a good like winter as well, in case I don't do assistance requests for you, because today's the last day for y'all. Okay, it's Friday. Yeah. Well, I mean, I've always thought of like December as the only month of winter. Like, have good holidays, right? It does start. Yeah, today's Yalda. Yeah. Are you having like a Yalda dinner and stuff? Oh. Okay, well, same thing. Yeah. Christmas Yalda, yeah. For those who are not Persian, there's a Persian night today. Yeah. Yeah, we just go like, oh, I'm Persian. No, it's the first day of winter. So, yeah, Persians are really into the first day of seasons. Yeah. Yeah. No, that's in the spring. Yeah.
Actually, can you look at line 52? Not in this one, in your notes. Like,
Yeah.
it's called. You didn't talk about that. What's
Yeah, so the CIA triad here, it just doesn't really fit into the context of the other stuff, but it's confidentiality, integrity, and availability. These are like I can send you actually
guidelines for
guideline for like what
the ID sector, I guess?
yeah, exactly. Like you want things to be confidential would be like private. Integrity being like every time you access, like it's going to be reflecting like the truth, right? And then availability in the sense of like if you're supposed to have access to it, it should be available to you, and like also relates to uptime. I can send you the slides that I have from my web-based info class that I took recently, where CIA triad is in here, and then they talk about a couple of different security principles. And there's a thing called OWASP 10 every couple of years that say like what are the current most critical web risks. So if we were to look at it for like 2018, top 10 vulnerabilities of this year
Okay,
would be like
that sounds good.
yeah. So I'll send y'all a link to this as well right now. It's gonna take me like a minute to compile the notes. Yeah.
Yeah,
Cool. Yeah. Call in the CIA triad. Yeah. OWASP. It's the Open Web Web Application Security Project.
Okay.
Yeah. Cool. And I keep thinking of the Amazon video where they drive out the car. Like, yeah, sorry, the truck. Yeah, the big old semi. It's a bit bigger than a car.
I don't know, I find it kind of fucking cool, man. Like,
It's awesome. Yeah.
There's a fucking truck, which is a hard drive.
Yeah.
Imagine, you're just fucking driving liquid gold. Like,
Yeah.
data is liquid gold, man.
Yeah.
And you're.
I find those like launch conferences hilarious. Like, have you seen the old ones from Windows with like Steve Ballmer?
Yeah.
Sweaty and just going like, yeah.
Developers. Yeah, a million times. Have you seen it? Oh,
you gotta
you're in for a treat. If you Google the word developers,
Okay. This guy like took down fucking Microsoft, right? He used to be CEO of Microsoft, right?
yeah.
Why is he spreading like a pig?
The early 2000s were a weird time.
Yeah.
No wonder he got kicked out of
Yes.
the board.
Actually? No way.
Well, he eventually got kicked off, right? Of the board or something?
I mean, this is
What is he doing?
he's hyping people up because the question is, what is the most important value? What is the most like valuable resource for companies like Microsoft, right? And he's like developers. Now it's data. But it used to be like developers because like developers are the people making the stuff that works on top of the Windows platform that adds value to the Windows platform.
I think even more important than data is how to fucking keep it, secure.
Yeah.
Like, you can have data. Like, getting data is not hard anymore, right? I
No,
mean,
you just keep
there's so many
grabbing.
like shady websites and like, places who actually sell